So this week's lab was called Analysis of Ethanol in Vodka. The goal of the lab was to analytically calculate the ethanol content in 40% or 80 proof vodka using IR and Raman instrumental methods, and to then determine whether IR or Raman was a more effective method for this calculation. So for our sample preparation, in the first week we did infrared spectroscopy, and we made up 5 different samples. Each had 25 milliliters of the 80 proof vodka, and then each had 1, 2, 3, 4, and 5 milliliters of 100% pure ethanol, and the remainder of the volume was milli-Q water added to a total volume of 50 milliliters. The reason why we did it this way with standard additions of pure ethanol was that the vodka content in the 80 proof vodka is too low for analytical calculations, so adding standard additions allowed us to back calculate later on the actual ethanol content in vodka. In week 2, the Raman spectrometer is a little bit less sensitive on the low end of the detection scale. So in addition to the standard additions of 1 to 5 milliliters of ethanol, we also did 4 additional samples which had 10, 15, 20, and 25 milliliters of the 100% pure ethanol. So this was the first IR spectrum. This was gotten from the first week. As you can see, there's a peak at 1,050 wave numbers. And as you can see, there's a lot of lines on top of each other, and what those lines correspond to are varying concentrations of ethanol. So I don't have a pointer on this PowerPoint, but at the peak at 1050 wave numbers, if you can see, the lowest peak is lower concentrations, and the higher peaks are higher concentrations of alcohol. And we'll see in the data in a minute that higher concentrations of ethanol correspond to higher peak intensities. So this is our data. In the first column, we have the volume of the pure ethanol standard added to each sample. The SF is then the fixed ethanol when you account for the pure ethanol standard and the ethanol in the vodka. And then the really important thing to look at is we made 2 measurements of the IR spectrum. We calculated the peak height for each concentration of ethanol, and we also counted the peak integral to see if one measurement versus the other gave a better result. And so here, plotted on this graph, we have a graph that shows SF, which is ethanol concentration, versus peak height. And as you can see, the best fit line has a slope of 0.1316 and a intercept of 0.5523 and an R-squared value of 0.99158. So that's very linear. To the left of the graph, we have the linear regression calculations done in Excel. You can see the top 2 values are the slope and the intercept. And then with the calculations with help from the Harris Quantitative Chemical Analysis textbook, we were able to do standard addition calculations to back calculate the percent ethanol in the vodka. And as you can see, we got 48.94% plus or minus 2.45%. So we are slightly over calculating by 8% the ethanol content, because we know that the vodka is supposed to have a 40% alcohol content. We did the same thing, but instead of calculating it with peak height, we did it with peak integral, and the calculated percent ethanol in this one was about 30% ethanol plus or minus about 0.5%, and I'm not sure. The way I calculated the standard error was I did the standard deviation divided by the total molarity of ethanol, It's 0.57%, seems a little bit low, but the important part is that the calculated ethanol percentage is about 30%, which is instead of on the high end, we're 10% lower than we want to be. Did the same calculations, but this time using Raman scattering instrumental as an instrumental method, and we never actually got a picture of the spectrum from this week, but I can tell you that the peak that we used to calculate the data was from 882 wave numbers. And then we're doing the same calculation here. We have the standard concentrations, and then Raman counts, instead of counting absorbance, it measures scattering. And so the measurement we're looking at is the, I think it's photon counts in the far right column. And then the data analysis, you can see that the data is not as great. The R-squared value is 0.72. It looks like there's not a lot of linearity in the bottom end of at lower concentrations, which is why we made up higher concentrations going from 10, 15, 20, and 25 milliliters of added standard. And here we have that calculated percent ethanol as 82.7% plus or minus 6.41%, which is really, really off. It's about twice as much as we would expect. So as you can see, the Raman data analysis was not as great. If for some reason we were to divide 82.7% by 2, we would get the expected 40%, but I don't think that's how this works. So you can see that the calculated percent ethanol is pretty off for the Raman data analysis. And so when we're looking at the comparison of methods, the difference between IR and Raman is that IR is measuring absorption, and it's measuring a change in the dipole moment of various bonds in the molecule. Whereas on the other hand, the Raman instrument is measuring scattering, and it's measuring the change in bond polarity. IR has the benefit. IR, unfortunately, you can't easily use aqueous solutions in IR, so we had to use an ATR in order to use water as the solvent, whereas Raman, the sample preparation, is a lot easier. As you can see from our data, where we had 30 and 48% ethanol content, the IR was a lot more accurate and precise than the Raman measurements, although not quite accurate since we didn't pinpoint 40%. It was definitely more precise than the Raman measurements. As far as sensitivity, the IR, well, I guess the Raman instrument was a lot more sensitive to use. We had to turn the lights off in the room. We couldn't bump into the instrument. The sample preparation, it's a little bit simpler of an instrument, but it was way more sensitive to background disruptions. At the same time, though, the IR instrument is only 1 year old. The computer system was really fancy, whereas the Raman instrument is way older than that. I think someone said it was about 20 years old, and the technology in the computer was not nearly as advanced as that in the IR. In terms of wave numbers, the IR is really only capable of measuring wave numbers as low as we scanned the whole spectrum down to 400 wave numbers, but really it was really the low end of the threshold is around 1,000 to 800 wave numbers, whereas the Raman we could get down to about 300 to 400 wave numbers. In my opinion, I thought the Raman instrument also required a little bit more expertise on behalf of the user. That may have also been because the technology was a lot older in that instrument, and so it was a little bit less user-friendly. The IR was also a lot shorter per sample, whereas the Raman took a little bit longer per sample. We had to take multiple measurements, and it took a little bit longer to get going. So if I were to say which method is better, in this lab, I would say the IR was a lot better to use. The results were a little bit more reliable than the Raman instrument, but at the same time, the IR instrument is less than a year old, whereas the Raman instrument is way older. So maybe it's not completely fair to judge them on the same playing field. Then we use web mode to calculate the normal vibrational modes, um, the theoretical normal vibrational modes of ethanol. In the far left-hand column, we have the theoretical frequencies in wave numbers, and we adjusted the IR values by multiplying by 0.9 to get the adjusted IR frequency values in the second column. The thing to note was that not every theoretical value was IR active, nor was every one Raman active, and the same peaks that were IR active were not necessarily Raman active. For the IR instrument, we measured the peak heights and integrals at the 1050, at the peak at 1050 wave numbers approximately. For the Raman spectrum, we measured the peak heights at 882 wave numbers. We probably should have done them both at the same frequency, and maybe we could have picked a frequency that was both IR active and Raman active and measured them at the same frequency. And then in the far right column, we have the various stretching and bending and wagging, what each frequency corresponds to. That was really me just looking at the videos and trying to figure out which one it was, so I'm not sure how accurate those descriptions are. At the end of this, I'll show you the stretching and the bending in the movies on Webmo. So here we're looking at the theoretical infrared spectrum and the experimental IR spectrum. It's kind of hard to compare them directly because we have, in the theoretical, it's kind of looking at it from top to bottom, and then it's flipped in the experimental data. But as you can see, we're measuring the peak height at about 1050 wave numbers, and that same peak height is there in the theoretical spectrum. As you can see also, what was theoretically supposed to be active was not necessarily experimentally observed to be active. If you look at the experimental spectrum, we have about 4 active peaks. In the IR spectrum, we have a few more than that. But then if we're looking at the theoretical versus observed IR values, those that were observed experimentally lined up pretty well with the theoretical values. So we have a slope of about 1 and an R-squared value of 90.9977. So that was good. Unfortunately for the Raman, we did not capture a screenshot of the experimental Raman spectrum, nor did we note what were the wave numbers of all the peaks, and so the only thing I have to show you is the theoretical Raman spectrum. But as you can see, there's a peak that's a tiny peak that's down close to about 1,000 wave numbers. That's the peak that we measured in our experimental data, and I'm assuming the reason why we picked that peak was because it's not a very intense peak. So with increasing concentrations, we could measure differences. Whereas if we had picked the peak that was at 3,200 wave numbers, we wouldn't be able to. It was so intense to begin with that measuring differences in concentrations would be a lot harder. This also just shows the IR and Raman spectra for water. The thing to note is that it's a lot harder to measure the IR spectra for water because we have this really intense peak at around 1,800 wave numbers that we don't have in the Raman spectrum, and that peak the intensity of that peak kind of just throws everything off. So that's why it's a lot easier to theoretically take the spectra of aqueous solutions with Raman spectra as opposed to IR spectra.